Good afternoon. I welcome you all to JCSF Charity Support Foundation online tutorial class. We are your humble master, GS. So, as we have been doing, I'm in charge of physics. So, and we are continuing this year from where we stopped last year. So, for those of you who have been following me right from beginning, we did a lot under physics. We've explained what physics is. We've talked about the fundamental and derivative quantities and units. We've explained that. We are on motion. We talk about what motion is, the linear motion. We talk about frictional forces. This afternoon, we will be talking about circular motion. As written on the board, we will be talking about circular motion. And when we talk about circular motion, we talk about, previously we talked about the linear motion, and that is the motion in a straight line. And there's no way we talk about the linear motion without talking about the circular motion. So, and when we talk about circular motion, we are going to explain what it is, and we explain the graphical representation of circular motion. Now, we talk about circular motion is a motion in a circle path in which the speed of the body remains constant while its direction continuously changes. In circular motion, the speed of a body remains constant, but the direction keeps on changing. We don't expect a body that moves from this side. The body will move on the same direction, on the same speed, but the direction will be changing. And that is what a circular motion is talking about. And what are the examples of circular motion? Number one, a racing car moving around a circle track. For instance, when a car moves in a roundabout, let's say that this is a roundabout, this is a highway. A car moving from here needs to pass through here, like this. There is probably that the car may be going like this. So that is one example of a circular motion. A racing car moving around a circular track. Another one is a stone moved in a horizontal circle. A stone moved in a horizontal circle. When you tie a stone, maybe to a thread, and hang it on its horizontal and move it, so it will definitely move in a circular path. And that is another example of a circular motion. That's another example of circular motion. Another example is planets going around the sun. Planet going around the sun. It's just stand at one place while the planet move around it. It's another example of the circular motion. And also the earth moving around the sun is also another example of circular motion. So let's look into some graphical representation to back up what I'm trying to explain about circular motion. Let's assume so these are the objects. Let's say the body. So the velocity of the body. This is A, B, C. All of them are up. So just take it this way. This is C and the velocity of C. Now, what am I trying to say here? When a stone is tied to the end of a rope and moved in a horizontal circular path, so the direction is constantly changing as the stone moves around the circle. So as the stone moves around the circle, the direction keeps on changing. So, but the speed of the stone is constant. The speed of the stone is constant, but the direction will keep on changing as the stone moves and the what? So the body. The direction of the stone will keep on moving, will keep on changing all the time as the stone keep on moving. As the stone moves, the direction keep on changing, but the speed will remain the same. So what am I trying to explain? It implies that velocity changes as the stone moves around the circle. The velocity of the body will change as the stone moves around the body, while the speed will remain constant. So let me explain again. When we tie a stone, let's say that the object remains the same, the velocity will be changing as at the beginning, the body may maintain the same speed, but the direction keep on changing. So the direction is constantly changing as the stone moves around the circular path. So the speed is constant. The speed by which the body moves around the circle is constant, but the direction keep on changing all the time as it moves. So, and that shows that velocity changes as the body moves around the circle. That is what we need to understand about the circular motion. What we should know under this is that under circular motion, the speed of a body remains the same while the velocity changes as the body moves around the circle. As the body moves around the circle. So let's now talk about the angular velocity. Angular velocity. Okay. Let's illustrate this in diagram before moving to explain anything about it. Center of the circle. Here should be our theta. So that in this place should be A, speed B. So now theta, this is the velocity. Now, let's talk about the angular velocity. We just explained what the circular motion is. We've talked about circular motion that, so it is a motion in the circular path in which the speed of the body remains a constant while its direction continuously changes. The direction here now is the velocity. So the velocity keeps on changing. So I will try to explain that. Now, let's talk about the angular velocity. the velocity that has been changing. What's the angular velocity? So let's use this to explain. Angular velocity is defined as the change of the angle per second. The change of angle per second. That is what angular velocity is all about. So angular velocity is measured in rad per second. Rad per second, or rad second raised to power -1. Now we can prove this from this. The angular velocity W is equal to theta all over the time. All over time. Let's assume this as equation 1. Angle and the time is take. So this one as equation 1. Now, when we cross multiply this, theta will be equal to WT. Now, therefore, this as equation 1. So in moving through an arc, So in moving through an arc, or S of a what? Of a circle. So the radius of the what? Of the angle. The radius of the angle moved is theta. Now, what I'm trying to say, in moving through an arc, so S of a circle, S of a circle, the radius of the angle moves is theta. The radius of the circle is this theta. So as represented in the what? In the diagram. So, and if the radius of the angle moved is theta, so therefore theta, I don't know if this is visible. Therefore theta will be equal to S all over the radius. So S all over the radius. With this now, we can cross multiply. This will be equal to S is equal to R theta. So S is equal to R theta. Then this will be equal to equation 2. So we're trying to prove the equation of angular velocity. So we're trying to prove the equation of angular velocity. Now, I would have liked if we have enough space, but you should all have seen the circle. So I have to keep on proving the formula. The formula, the equation of angular velocity. Now, S is equal to R theta, and that is equation 2. So when we divide it through with T now, that is dividing equation 2 through T. Dividing through T. Dividing in the diagram. divided through with T, sorry. Divided through with T. Then this will be S over T is equal to R theta all over T. So dividing equation 2 by T, S all over T equal to R theta all over T. This is equal to R times theta all over T. Therefore, velocity will be equal to RW, which is equation 3. So let me come and explain this clearly. So we say here that in moving through an arc, if you look into the circle, in moving through an arc, in the circle is an arc, an angle. So in the angle is theta, in the arc is S. So we say in moving through an arc, S of a circle, the radius of the angle moved is theta. The theta is in the angle. Therefore, we say theta is equal to S all over R. So we divide, we cross multiply. When we cross multiply, the S will be equal to R theta. And that was how we arrived at equation 2. So by getting the equation 2, dividing through with T in equation 2. And don't forget that equation 2 is S is equal to R theta. When we are dividing through equation 2 now, the S all over T is equal to R theta all over T. And that is what we did here. So S over T is equal to R theta all over T. So result in R times theta all over T. And do not forget that our theta is WT after equation 1. Theta is WT after equation 1. So, and our velocity is S all over T. Is that we are like this, and therefore V will be equal to RW. So, which is equation 3. Now, let us move on. Now, that is equation 3. Hence, the period T of the motion, the period T of the motion in the angular velocity, in the angular motion of the motion, so is given as the period T of the motion is given as, that is T is equal to 2 pi all over the W, which we can regard as equation 4. So the period T is given as 2 pi all over W. That is the period T, 2 pi over W. So analyze equation 4. Now, W is equal to 2 pi force of attraction. Force of attraction, we talk about force of attraction under the frictional force. So W is equal to 2 pi force, which is the same thing as T is equal to 2 . T is equal to 2 pi all over W. So, which is equal to 2 pi over W, is equal to 2 pi all over W, 2 pi F. W is 2 pi F. So why the 2 pi is the 2 pi? So our W is 2 pi F. So why W is 2 pi? And that was why we come into 2 pi all over 2 pi F. So 2 pi here we give you 1. 2 pi here also we give you 1. This will give us 1 all over F, which is our equation 5. So to make this angular velocity clear, for those of you who are following me, I think I will have to recap and explain more about it, so you can get the content of the lesson. So in the diagram I draw, there you see an angle in an arc in the circle, where the two ends of the angle are A, B, and 0. Theta, the arc is S. That is the length of the arc of the angle is S. And there's an inclined angle at the outside, where we also have theta and velocity. So the direction of the body, the distance it moves, velocity at the down in the diagram. So another is the angular velocity is the change of the angle per second. So angular velocity is the change of angle per second, and it is measured in radius per second. So we try to prove the equation of angular velocity, and that we say, so W is equal to theta all over T. W is equal to theta all over T, and that is equation 1. Our W now is theta all over T. So we can now cross multiply, and when we cross multiply, that will give us theta, which is equal to WT, according to what we've written so far. Now, in moving through the arc, the S in the arc of the circle of the radius of the angle moved is theta. The S of the circle's radius of the angle moved is theta. So theta is equal to S all over the radius, because the S of the circle, the radius of the angle moved is theta. And theta is the angle. Therefore, theta is equal to the S all over the radius. And when we multiply, when we cross multiply theta, which is equal to S all over R, we end up with S, which is equal to R theta. S is equal to R theta. And that was how we arrived at equation 2 here. Theta, which is equal to S all over R. So when we cross multiply, S will be equal to R theta. That was how we got equation 2. Now, we started dividing through with T in equation 2. Our equation 2 is S is equal to R theta. Dividing through with T in equation 2 now. This is how we're going to get S all over T is equal to R theta all over T. I want to work this out. It's going to give us R times theta all over T. So our V is equal to R W. So our V is equal to R W. And we see the location of the V in the diagram. We see it is the change of the body. So the change of the body, so, and that is radius W. That was how we got V is equal to RW, which is equation 3. Hence, the period T of the motion is given as period T of the motion. It's given as T is equal to 2 pi all over W. This is given. T is equal to 2 pi over W is given. And this serves as the equation 4. Therefore, W will be equal to 2 pi F, which is what? The frictional force of the what? Of the body. So the frictional force of the body, 2 pi F. Then T will be equal to 2 pi W, as given here, which is equal to 2 pi all over 2 pi F. How do we get 2 pi over 2 pi F? So the 2 pi here is the 2 pi W. Our W is 2 pi F, and this is 2 pi F. 2 pi, we cancel 2 pi, and that will give us 1 all over 4, which gives us the equation 5. So with that, I think we've explained some little about the angular velocity. Now, when we want to talk about anything now, before moving to the main calculation now of motion now, the only thing that's remaining is centripetal force. The centripetal force, which we need to explain. Centripetal force, we've already clear with the angular velocity. So we can talk about the centripetal force now. Centripetal force. This is still under the circular. It's still under a circular motion. So let's start with the centripetal force. What is centripetal force? Centripetal force. So let me use an object, for example, to explain a centripetal force. For instance, when a stone is attached to a string, so and it moves around at constant speed in a horizontal circle. So when a stone is attached to a string and moves around at a constant speed in a horizontal circle. So the stone moves with a constant speed, but a different direction, an acceleration directed toward the center of the circle due to the tension in the string that produces a force. Okay, for those who is not getting it right, we're trying to express centripetal force, and I'm trying to use stone as an example to explain a centripetal force. And I say when the stone is attached to a string and move around at constant speed in a horizontal circle. So the stone that moves with constant speed, but at different direction, we've explained that under a circular motion. When the body is moving with the same speed around the circle, the direction will be different. That is, the velocity of the body will be different as it moves around the circle. So I'm just trying to move back to that so you can get to understand clearly what I'm trying to say. So when the stone is attached to that string and we move the string around at constant speed in the horizontal circle, the stone moves with constant speed, but at different directions. An acceleration A directed towards the center of the circle due to the tension in the string that produces a force. Let me repeat. The stone moves with a constant speed, but at different directions. We have already know that as circular motion. With constant speed, but at different direction. An acceleration A directed towards the center of the circle due to the tension in the string that produces the force. So the acceleration is directed toward the what? The center of the circle. And this is due to the tension in the string that produces the what? A force. Hence, we can say the acceleration is equal to velocity of the body, which is equal to radius raised to the power 2. You know, when we say VW, and which is R raised to RW squared, I will run down because now, so acceleration is equal to velocity of the body is equal to radius of the body raised to power 2. Now, this is equal to velocity squared all over R. So whereby W will be equal to V all over R. A is equal to V W, which is implied as R W squared. Now, this is velocity squared all over the R. We don't need to take care. Velocity squared. So all over R. This is equal to W. W will be equal to V all over R. So that is the force that is required to keep this object, that is the stone, moving in the circular path is called centripetal force. Now, that force that is required to keep the object moving in the circular path is what we refer to as a centripetal force. But something must direct it toward the center of the circle, and that is what? Acceleration. So the acceleration that directs toward the center of the circle due to tension in the string that produces the force. But the force, that force that is required to keep the object or the stone moving in the circular path is what we refer to as centripetal force. Thus, we can say that the force is equal to ma, as we have already know. So mass times acceleration. And don't forget that our acceleration here now is VW. So therefore, force will be equal to mass acceleration VW. Our VW is, our acceleration is RW to the power 2. Therefore, force will be equal to NRW squared. Which will now produce the V squared over R. RW squared produce V squared over R. And this will be, force will be equal to, the centripetal force will now be equal to mv squared all over R. That is the formula of the centripetal force. Before our class round up, let us try to look into a calculation. We're going to be having a little minute. Then we move on in our calculation deeply in our next class. Example. An object so of mass 4 kg, moves in a circle at radius 8 meters at uniform speed of 32 meters per second. Calculate. I hope the time should permit us. I hope it doesn't permit us. We continue with the calculation in our next class. Calculate A, the angular velocity, and B, the centripetal force. So let's quickly look into the solution. without wasting much of our time. So given that in the question, given that mass is equal to 4 kg, so radius is equal to 8 meters, and v, velocity, which is equal to the what? The speed. So, which is 32 meters. 32 meters per second. So, the angular velocity now, A, the angular velocity. Do not forget that our angular velocity, W, is equal to V all over R. And our V is 32, velocity is 32 meters per second. That will be 32 all over radius what? 8. Now, this will give us, for the unit of the angular velocity is rad per second. So that is for angular velocity. Now, because our angular velocity is v, velocity all over radius, and velocity is there, and radius is there too. So with that, we get the solution of the angular velocity. Let's now calculate the centripetal force. Let's calculate the centripetal force, which is B. So I want to quickly, centripetal force is equal to mass, so R W squared, and which is equal to, our mass is what? 4, according to what given the question. So times radius, which is 8, and the body. The body is what? 4. But W raised to power 2, 4 is power 2. Now, this will give 4 times 4 will give us 16. This will be 4 times 8 times 16. If we do the calculation, 4 times 8 will give us 32. 32, 16. 6 times. This will give us 512 Newton. That's our centripetal force of the body. So you can see how easy it is to calculate the angular velocity and centripetal force. Now, with that, we can come to the end of the lesson, and we continue with our work examples in our next class. So, mind you that our next class will be based only on the calculation regarding circular motions. So, thanks for the viewers, thanks for the chairman of the JCSF. We meet again next week, Thursday. I remain my humble self, JS. Have a wonderful day. Bye.